Hello, welcome to the first video for the online version of Math-321. This is going to be Investigation 23. So let's get started. So first, just a word about how these videos are going to work. I'm going to attempt to recreate the experience that we were having in the classroom where I would make you the notes every day and then we would go through the notes together and there would be activities. And then I'm going to ask you to try all the activities, pause the video and try them, and then I'll go over the answers to the activities, and that's what we'll do. Okay, so a couple of items from last time that are going to be relevant today is definition 22.13. So let G be a group, and let A be an element of G. Then the cyclic subgroup generated by A is denoted like this, angle brackets A. And that is defined, so there's two different definitions, one for multiplicative notation and one for additive notation. Normally we'll use the multiplicative notation unless we happen to know that we're doing addition for our group operation. So angle brackets A is defined as all of the integer powers of A. That's if the group operation is multiplicative. And then otherwise, if the group operation is additive, angle bracket A is defined as all the integer multiples of A. And that element A that's in the angle brackets, that is called the generator of the group because it generates the group by making all of its powers or all of its multiples. It makes the whole group. Note also that an alternative definition is that angle bracket of A is the smallest subgroup of G that contains A. And the other definition that's going to be relevant today is definition 22.14. A group G is called a cyclic group if G is in fact angle bracket of A for some element A in G. Okay. So the focus questions for this investigation are the following. What property must be satisfied by all subgroups of a cyclic group? What is the subgroup structure of a finite cyclic group? What is the subgroup structure of an infinite cyclic group? And what important properties does the order of an element in a group have? Okay, so let's talk first about the Zn family. So the family of groups denoted by Zn with the operation of addition and with n being a positive integer, those are the canonical examples of finite cyclic groups. In fact, for each positive integer n, Zn is actually the only cyclic group of order n. And I'd like you to recall that every element in Zn has the form bracket k sub n, and that can be also rewritten as k times bracket 1 sub n. So what that means is actually that 1 sub n, bracket 1 sub n, that is the generator of Zn. And we denote that it's the generator like this, Zn equals angle bracket, bracket 1 sub n. So we know that already about Zn, but what we are going to investigate in this section is what are the subgroups of Zn like. So let's get into that with the next activity. Okay, so preview activity 23.1. So I put here the entire activity for you, and I'd like you to go ahead and try the activity before we look at the solutions of it together. So go ahead and pause the video and give that a try, see how far you get. Okay, and now let us go over the solution to preview activity 23.1 together. So, let H be a non-trivial subgroup of Z100. So note that the group operation here is addition. That's going to be the case for all of these Zn groups. The operation is always addition because they're not going to be groups under multiplication. And furthermore, non-trivial here, I could not find where we had actually defined that before, but that means that H is not the subgroup consisting of only the identity element. So that subgroup of only the identity element, that's actually a subgroup of every group, and that's called the trivial subgroup. So by non-trivial, they just mean that that's not H. H is not just the identity element. Okay, so part A, suppose that bracket 20 is in H. Or another way to say is this is the congruence class of 20, modulo 100. So suppose that that is in the subgroup. List at least 3 other elements that are also in H. And what is the smallest number of elements that H can have? Explain. Okay, so other things that would be in H. So first of all, H is a subgroup, which means that it's a group. So 0, bracket 0, that's going to be in H. Again, H is a group, so it's going to contain inverses, so negative bracket 20 will be in H, and negative bracket 20, that's the same as bracket negative 20, which is the same as, we can add 100 and say that that's actually 80, so that's going to be in H as well. What else is going to be in there? Well, the group is closed under the group operation, which was addition. So we can definitely say that 20, bracket 20 plus bracket 20, that's in the group. So 40 is in the group. And same deal to get 60. That will also be in the group because of addition. So 20 plus 20 plus 20, 60, that will be in the group. Okay, in fact, if you think about it, you can add or subtract 20 as many times as you want from 0 or from itself or from any of these other elements that we've listed here. So, in fact, k times bracket 20 is going to be in the subgroup H for all integers k. Okay, and that's again because H is closed under addition. All right, so that takes us to part B. If bracket 20 is in H, must it be true that H contains angle bracket, regular bracket 20? There's too many brackets here. That will in fact be true because that's what we just said on the last part A. So angle bracket, square bracket 20 is exactly the integer multiples of bracket 20. And that must be a subset of H because H is closed under addition. So we can add or subtract bracket 20 to bracket 20 as many times as we want and still land in H. Okay, so since, or rather if angle bracket 20 is in H, is it possible that angle bracket K, why am I saying angle brackets? Sorry, if bracket 20 is in H, is it possible that bracket K is in H for some integer K with 1 less than K and K less than 20? If so, in which situations could that happen? If not, why is it impossible? Well, this is definitely possible. I mean, H could be the entirety of Z100, in which case all of those numbers would be in there, because every group is a subgroup of itself. Some other possibilities would be H could be the group generated by 5, which would consist of 0, 5, 10, 20, and so on up through 95. And then 100 would be 0 again, of course. Etc. There could be lots of situations like that. I'll let you think about how many there might be. Okay, part D. Let S equal the set consisting of all positive integers k such that k times bracket 1 is an element of H. This is an interesting condition here. So they're asking us which of the positive multiples of bracket 1 are in H. That's what S is. So why is S non-empty? So we're not supposing here anymore that bracket 20 is necessarily in H. That was something that was given specifically in part A, B, and C, but not throughout the whole activity. So how do we know that S is non-empty? Is there anything else we know about H that could tell us that? So the only things we know about H are that it's a subgroup of Z100 and that it is non-trivial. So I think the only helpful thing there is that it's non-trivial. So H is non-trivial. And again, that means H is not just equal to the set that is only 0, the identity element. H is not just that. So there must be something else that's in H. I'll say it like this. There's some K in H, bracket K in H, for K. Let me see, how can I say this? Use my eraser. Where K has to be between 1 and 99. Okay? So that K would be in S. Okay, so part 2, what important conclusion can we draw about S as a non-empty subset of Z+? Remember, Z+ is the positive integers. So whenever you have a subset of the positive integers or the whole numbers, we have the well-ordering principle. So S has a least element because of the well-ordering principle. All right, and part 3, how do you think this important conclusion is related to H? What would be special about that least element of S? Well, the least element of S, I'm putting some question marks here. This is actually going to be related to the next activity that we're doing, but I think I'll let you think about it until we get to that. Okay, so let's look at subgroups of cyclic groups. So theorem 23.2 is that every subgroup of a cyclic group is cyclic. This is a really, really powerful and important theorem. Most groups, you really cannot analyze their subgroup structure easily, and if you could, it would give you a lot of very helpful and important information, but it's typically not easy at all. But cyclic groups, their structure is actually pretty easy to understand, and their subgroup structure is easy to understand. So every subgroup of a cyclic group is cyclic. We're going to actually prove this in the next activity. And just a couple of notes before we look at that. Note that if H is a subgroup of the cyclic group G equals angle bracket A, every element of H is going to be some power of A. That's what it means to be this cyclic group generated by A. That means that all the powers of A are the group. And then, so of course, every subgroup would also consist of powers of A. And then the problem, of course, that makes it a little bit tricky to prove this theorem is that it is not obvious which powers of A are going to be in that subgroup H. G has all the powers of A, but which of those powers are going to be in H? It's a little hard to find out. But let's go ahead and do it in the next activity. So here's the entire activity. It is really long, as you can see. Unfortunately, I made it even longer than it was. I added 2 things that were not in the textbook because I think their last item was kind of too hard to work out. So I made it a little easier on the last 2 items. But this is going to take us through the entire proof that every subgroup of a cyclic group is cyclic. So please go ahead and pause the video and give this a try, and then you can look at the solution. Okay, let's go ahead and look at the solutions together. So let G equals angle bracket A be a group. So that tells us that G is a cyclic group. It is generated by A, and so every element of G will be a power of A. So we want to prove in part A here that every subgroup of G is cyclic. So how do we write that more formally? How do we start? What do we assume to begin our proof? So I think what we should do is we should assume that H is a subgroup of G, and then what we need to do, our goal will be to show that H is cyclic. In other words, that H is generated by some element, maybe I'll call it B, where B is some element of G. Okay, let's look at part B. So let H be a subgroup of G. This is exactly what you need to assume to start the proof. There's one subgroup of every group that is cyclic. What subgroup is that? Well, what subgroup is that? So firstly, there's only two subgroups that you're guaranteed to have in any group, and that's the entire group, and then the group that's just the identity element. So the subgroup that's just the identity element is actually cyclic. Because if you just take every power of the identity, that's just the identity again. Okay. So we can assume that H is not this subgroup. What additional assumption does that allow us to make? So assuming H does not just equal the identity subgroup means, well, what does it mean? I guess that would mean there must be some other element in H. And remember, all of the elements of H, just like all of the elements of G, are going to be powers of A. So that would mean that there's some power of A that's in H, where that power of A is not the identity. So where k does not equal 0, since the identity would be a to the k, or sorry, a to the 0. Okay, so part C, let little h be in big H. Since little h is in G as well, the element little h must have a specific form, which is what? This is just what I was just saying in the last part B. So little h is going to look like a to the k for some integer a. Okay, and that's because G is generated by A. All right, let's look at the next slide. Okay, so continuing on with part D, let H be a non-trivial subgroup of G, and let S be the set consisting of all positive integers k such that a to the k is in H. So S is basically keeping track of all of the exponents of A that are in H. How do we know that S is non-empty? So this goes back to part B, which was on the last slide. We said that H is non-trivial, so it contains an element that is not the identity, and remember the identity is a to the 0. So it contains a to the k for some integer k that is not 0. So that k power, that would be in S. But wait a minute, how do I know that k would necessarily be positive? So I think I need a little bit stronger argument here, since S is only supposed to contain positive integers. Let's see. Then a to the negative k is in H as well, because H contains inverses. So a to the negative k would be the inverse of a to the k. And then either k or negative k should be positive. Okay, I hope that argument makes sense to you. Part E, what result tells us that S contains a smallest element? So again, this is just the well-ordering principle. Whenever you have a subset of the whole numbers that is non-empty, or a subset of the positive integers that is non-empty, that will have a least element. Okay, per F, let m be the smallest positive integer in S. That is, m is the smallest positive integer such that a to the m is in H. This element a to the m is a candidate for the generator of H. What must we do to show that angle bracket a to the m equals H? In other words, that H is generated by a to the m. So remember the definition of this angle bracket notation. This is a to the m, all the powers of a to the m, so a to the m to the k, such that k is an integer. That's what that notation means. So we would need to show, if we're going to say that that equals H, then for all elements, let's say little h in big H, little h equals a to the m to the k, which we could also write a to the mk if we wanted to, for some integer k. Okay, that would show that angle bracket a to the m equals H. All right, let's see if we can do it. Okay, so let's continue. Suppose that b is in H, so b is just some random element of H. Why does b have to equal a to the L for some integer L? Hopefully you understand this one. This is because g is generated by a. So because g equals angle bracket a, every element of g is a to the L for some integer L, and of course elements of H are also elements of G. Okay, part H, since m is positive, we can divide L by m and obtain a unique quotient Q and a remainder R. What result tells us that we can do this? That's the division algorithm. I hope you remember that one. What is true about the remainder? So the remainder is always supposed to be between 0 inclusive and the divisor non-inclusive. And the divisor here is m. And then what is the specific relationship between m and L? So we're always guaranteed that the number that we're dividing, which here is L, equals the divisor m times the quotient Q plus the remainder. Okay. And finally, part I, how do we know that a to the negative qm for any q in Z is in H? So this is because we assumed that m was in that S set. So that S set, remember, that was keeping track of all the exponents of a that gave us elements in H. So that tells us that a to the m is in H. And then once you know that a to the m is in H, then any power of a to the m also has to be in H, because H is closed under its group operation, which is multiplication. So since, So since H is closed under multiplication, a to the m to any power that's an integer will be in H. Okay, and then you can think of that negative on the Q, it's just giving you another integer. Or if you want to, you can argue that H also contains inverses. Because that's another group property. So a to the mq being in H would imply that a to the negative mq is also in H. That would be the inverse. Okay, let's move to the next slide. So part J, use the fact that a to the L equals a to the qm plus r, and that a to the L and a to the negative qm are elements of H to find that a to the r is also an element of H. This is where I had to break it down a little more compared to what was in the book to make it a little easier. Okay, so the fact that a to the L is an element of H means that a to the qm plus r is also an element of H. Okay, and then since a to the negative qm is another element of H, and H is closed under multiplication, that means that a to the qm plus r times a to the negative qm will also be an element of H. And I hope you remember that we learned a couple sections ago, maybe investigation 21, that if you have the same base, so you have a to some different powers multiplied together, a is always going to commute with itself, so we can just combine those exponents together. So what I'm going to do now is I can say that a to the qm plus r minus qm, which equals a to the r, is an element of H. So I've just simplified that big element that I got over here. And that gives me a to the r. So how does that help me here in part K? I'm going to argue from the fact that a to the r is in H to tell me that r actually equals 0. So remember that r is a remainder that we got from the division algorithm. So that means that r is between 0 and m, and it's strictly less than m. And remember, m is the smallest element of S, which is the following set. S is all of the positive integers k, such that a to the k is in H. Okay, so r has to be smaller than m, but m is the smallest element of S, where that's all of the positive exponents of a that are giving us elements in H. So taken together, what do those two things mean? Well, r definitely can't be a positive number, because if it were, that would be a contradiction. So r cannot be in the positive integers because it is smaller than m. And if r is not going to be a positive integer, I mean, look at its inequality that it's in. So it has to be 0. That's the only thing that's left for it to be. Okay? So now that we've proved that r has to be 0, that was actually the last step. Why does that prove that every subgroup of a cyclic group is cyclic? So what this tells us is that, remember where we originally got the r from? Remember we found that b was equal to a to the L, which was equal to a to the q m plus r. Now that we know that r is 0, we just have that that b is equal to a to the qm, which is going to be a to the m to the q. And remember, b was just some random element of H that we pulled out of thin air. So every random element of H is going to be equal to a to the m to the q, where m is that smallest element of S. So that is why we have proven that every subgroup of a cyclic group is cyclic. And in particular, the generator is going to be this a to the m. That is the Sorry guys, I can't spell tonight. So a to the m is going to be the generator, of H. And remember, B was just a random element of H. Okay, let's move on to the next thing. So next we're going to talk about the properties of the order of an element. So here we have definition 22.17. Let G be a group and let A be an element of G. The order of the element A in G is the order of angle bracket A. In other words, that's just the number of elements that are in angle bracket A. So basically what you do, you just take all the powers of A that exist, and you just count how many there are, and that's the order of A. Okay, so let's do a preview activity where we do this with some Zn groups. So the orders of the elements in Z4, Z5, Z6, and Z7 are given in the table over here. So we have Z4 is here, Z5, Z6, and Z7. And then we're looking at the order of these particular elements, bracket K, where K is given over in the left column. And the lines here, that's for the order. Okay, so that means the order. Line means order. Okay, so what you need to do is part A, complete the table, and then part B, they're going to ask you to make a conjecture. So I'll ask you to pause the video and give a try at this. Okay, so let's go over this activity. So first I'd like to point out that if you are trying to calculate the cyclic subgroup generated by 0, it really doesn't matter what your modulus is. This is just going to be all the multiples of 0, integer multiples of 0, and that's always just going to be 0. So that subgroup is always going to have an order of 1. It'll just have 0 in it. So these first two entries here at the top of the table are just 1. And then if you look at the next row, that one is kind of similarly predictable. So if we look at the order of 1 in Z8, so what do we get if we just try to write out all the multiples of 1? Well, first of all, there's 1. And then if we do 2 times 1, we get 2. And then if we do 3 times 1, we get 3. And it's not very exciting. You just keep going like that. And then you get 7. And then you do actually, if you go to the next one, you get 8, which is the same as 0. Okay, and then once you've got 0, you're really done. There's nothing else, because you got the whole group. Okay, so the order of that, so the cyclic subgroup generated by 1 in Z8 is all of Z8. So that's going to have an order of 8. And then 1 with modulus 9 is the same way. That's just going to give you Z9. So the order of 1 in Z9 is 9. Okay, now let's look at some of the rest of them, so they might be a little more interesting. So if we want to figure out the cyclic subgroup generated by 2 in Z8, so we're going to start with 2, and then 2 times 2 is 4, and then 2 times 3 is 6, and then 2 times 4 is 8, which is the same as 0. Okay, and then if we keep going like that, we make more and more. We could get 2 times 5 is 10, but that's the same as 2. So that's really all of them. And then if you want to go in the negative direction as well, you'll just also find that you keep getting the same ones that you've already gotten. So there's only 4. Let's try just doing a few more, and then I'll just kind of write in the rest of them. So 2. All right, so 3 in modulus 8. This one is maybe slightly more interesting. So you start with 3, and then 3 times 2 is 6, and then 3 times 3 is 9, but 9 goes back down to 1. And then 3 times 4, that's 12. And that goes back down to 4. And then 3 times 5 is 15. But that goes back down to 7. And then 3 times 6 is 18. And that goes, well, that goes all the way down to, let's see, we don't just subtract 8, we actually have to subtract 8 twice. And that takes us all the way back down to 2. Okay, and let's see, how many elements have we got so far? 1, 2, 3, 4, 5, 6. I think we can do a couple more. So 3 times 7 is 21. And again, if we subtract 16, that takes us back down to 5. And then 3 times 8 is 24. And then we're going to subtract 8 3 times, and that's going to take us all the way back down to 0. And at this point, we've got the entire group. Okay, so that was all of Z8. So this one is going to have order 8. Okay, I think I'm going to let you do the rest on your own, but I'll just fill in what these numbers here should be. I'll kind of do them in my head really quickly. So 4, let's see, that's going to give you 4, and then 8, which is 0, so that's 2. 5, that's going to give you the whole group. 6 is, I believe, going to give you the same as 2, so that should be 4. 7, that's going to give you the whole group. And then 8 is the same as 0, so that's going to be 1 again. Okay, and then for Z9, 2 is going to give you the whole group. 3 is going to give you 3. 4 will give you the whole group. 5 will give you the whole group. 6 should give you 3. 7 should give you the whole group. And then 8 should give you the whole group. Okay, and then in the next activity, you'll see why I kind of like know those numbers off the top of my head for some of them. Okay. Okay, so let's go ahead and fill in these entries again quickly, and then we can talk about this. Okay, so let's look at part B here. So there's actually an explicit relationship, an explicit formula that tells you the order of each element in a group, but it's kind of hard to see. There's a few patterns that you can see here in this table. Like for example, you always get 1 across the top. So the order of the identity element is always 1. And then the order of the group generator is always just obviously the size of the group. But other than that, it's kind of hard to see what it might be. One thing you could note is that everything in each column is a divisor of that column's modulus, so that's interesting. And furthermore, when you have the modulus being prime, you do get that everything except the identity element is having the same order as the modulus. So 5 here is also the identity element in Z5. And here we get all 7s, oops, all 7s here, and then all 7s down here. And again, 7 here would be the same as the identity in Z7. So that's interesting to note. Another thing you might note in the column for Z9 is that only 3 and 6 are the elements that don't have an order of 9, aside from the identity element, of course. And 3 and 6 are also the elements that are not relatively prime to 9. In other words, they share a factor with 9. So I'll let you think about that a little bit, and then we will actually give the explicit formula later on in the lesson. Okay, theorem 23.5. So this theorem says let G be a group with identity E, and let A be an element of G with order N. So again, that means that if you would take the group generated by A, the order of that group, the size, the number of elements in it is N. Then we get the following two results. A to the N is the identity element, and moreover, N is the smallest positive integer such that A to the N equals the identity element. And then secondly, if S is some other integer such that A to the S equals the identity element, then N must divide S. In other words, S has to be a multiple of N. So this is pretty interesting, and it's not too hard to work out why it's the case, but you should read through the proof of this theorem in the textbook. We're not going to do it here. Okay, so now let's think a little bit about the order of subgroups. And this is going to take us back to that part B that we were trying to think about in preview activity 23.4. So theorem 23.6 says let G equals angle bracket A be a cyclic group of order n, and let K be an integer. Then we have the following two results. So the cyclic group generated by A to the K is actually exactly the same as the cyclic group generated by A to the GCD of K and N. And that's interesting. Not necessarily an expected result, but we did see, for example, previously we saw that in that preview activity, the cyclic subgroup generated by 6 mod 9 is actually the same as the one generated by 3 mod 9. And the GCD, of course, of 6 and 9 is 3. Okay, and so in that activity that we were doing, we were using additive notation. So 6 is basically like A to the 6, where A is 1, and 3 is basically like A to the 3 because we were using additive notation. So that would be an example. And then the second thing that we get from this theorem is that the order of the cyclic group generated by A to the K is going to be the modulus n, the order n of that group G divided by the GCD of K and N. So that's another thing that is quite interesting. And for example, we did see that the order of the cyclic subgroup generated by 6 in Z9 was 3, which is 9 divided by the GCD of 6 and 9, which is 3. Okay, so that was actually the formula that was at play there. And you should read through the proof of that theorem in the textbook. It's interesting and worth knowing. One of the other interesting consequences of this theorem is that A to the K will only be a generator of G if and only if the GCD of K and N, which again, N is the order of G, is 1. So if you have any element in a cyclic group G and its exponent has a GCD that is relatively prime to the order of the group, then that element will generate the group. Okay. So now let's talk about finite cyclic groups, and what we're going to do is we're going to be able to completely classify all of the subgroups of a finite cyclic group. And so the theorem that does this classification is this one, 23.7. Let G be a finite cyclic group of order n. For each positive divisor m of n, there is exactly one subgroup of G of order m, and these are the only subgroups of G. So this theorem, it completely tells us what all of the subgroups of these finite cyclic groups look like. First of all, they are themselves cyclic groups, and their order has to divide the order of the larger group. And so the next activity is going to show us how to prove this. Okay, so here is activity 23.8, so go ahead and give this a try, and then we will go over the answers. Okay, so let's go over the answers here. So let G equals angle bracket of A be a finite cyclic group of order n, and let M be a positive divisor of n. So part A used theorem 23.6 to find a subgroup of G of order m. This shows that G contains at least one subgroup of order m. So this is a little bit tricky, but let me show you how to do it. So we've assumed that m is a positive divisor of n. So what that means is that there exists some other integer, we'll call it k, such that k times m equals n. Okay, and then what I'm going to do is I'm going to show that a to the k, the subgroup generated by a to the k, where k is that number that I just defined, has order m because, so here's where we're going to use theorem 23.6. So theorem 23.6, oops, I think I made a typo when I copied and pasted it. It should have these little lines here. So because a to the k, that order is going to be n divided by GCD of k comma n, and that is going to equal, so we said already that n equals k times m. So this is going to be k times m over GCD of k, and remember n is also k times m. So what is the GCD of a number and then another number that's a multiple of it? Whenever you have a number like k and then another number that's a multiple of it, like km, the GCD between those two numbers is just going to be k. Okay, it's just like between 2 and 8. 8 is a multiple of 2, and the GCD is just 2. And that's always the case when one of the numbers divides the other. So this is going to be km over k, which is just m. Okay, so this cyclic group a to the k that's generated by a to the k is going to have order m. So G will contain at least one subgroup of order m. Okay, so let's look at part B here. Now suppose that G contains subgroups h and k, which are both of order m. How can we conclude that h equals angle bracket a to the s and k equals angle bracket a to the t for some integers s and t? Okay, well, we know that h and k have to be cyclic, firstly, because we already proved that all the subgroups of a cyclic group are cyclic. Remember, that was that really long activity we did. So h and k must be generated by some elements from G. I'll just call those elements, I don't know, G1 and G2. So h and k are cyclic groups generated by G1 and G2 for some elements G1 and G2 from G. And then because G itself is generated by A, that means everything in G is a power of A. So G1 is, we can call it A to the S, and G2 we can call that A to the T for some S and T integers. Okay? All right, part 2. Explain how theorem 23.6 tells us that h equals k. What can we conclude about the number of subgroups of G of order m? Okay, so this is actually kind of complicated, and let me fix the typo on theorem 23.6. It's supposed to have lines there. Right, like I said, it's kind of complicated, but it's based on the fact that we know the order of these groups. So we know the following. We know that the order of a to the s, so that's h, remember, is equal to m. By assumption, we're told that the order of h is m. And we're also told by theorem 23.6 that the order of the cyclic subgroup generated by a to the s is n divided by GCD of, let's see, we're using s comma n. Okay, so that's one thing we know. And then we also know about the group K. So we were told K is equal to angle bracket A to the T, and we were also told that its order is M. And then by theorem 23.6, we also know its order is N over GCD Tn. Okay, so what do we get from this? Well, we can say from this that if we look at these two different equations that we've written here, m equals n over GCD of s and n, and m equals n over GCD of t and n. So conclusion there is that those two GCDs must be equal. Otherwise, those two equations couldn't both be true. So GCD of s and n must equal GCD of T and N. Okay, and then the next part's a little bit tricky to see as well, but now we can use part 1 of theorem 23.6. So I'm going to substitute in S for K. So the cyclic subgroup generated by A to the S is the same as the cyclic subgroup generated by A to the GCD. Again, I'm just substituting S for K, so this is GCD of Sn. Okay, and then if I use that part 1 again for T, substituting in T for K, I get A to the T equals A to the GCD T comma N. Okay, and we said that those two GCDs were equal, so if both angle bracket A to the S and angle bracket A to the T equal angle bracket A to the same number, then we get the following: angle bracket A to the S equals angle bracket A to the T. Like I said, that's a little tricky to figure out, but there it is. Okay, so part C here, explain how we have completely classified the subgroup structure of finite cyclic groups. So we found there is actually a subgroup of order M for all integers M that divide N. So we found a bunch of subgroups, first of all, and then we found that these are unique. There's only one of these subgroups for each integer M that divides N, and we found there are no other subgroups. So that was like a thorough assessment of all the subgroups. And why couldn't there be any others for numbers that don't divide N? That was because of theorem 23.6. Okay. Okay, everybody. Thanks for watching. I hope you felt like that went pretty smoothly. Hopefully they'll get smoother in the future. If you have any questions, have any concerns, need any help with the homework, just send me an email. We can set up video chat sessions to help you with the homework. You can share your screen. I can share my screen. We can write on a whiteboard together. And hopefully that'll be able to replicate the experience of coming into my office. Your next homework is the homework 6 that's due today, March 23rd. So I hope you've been working on that. And please refer to the email that I sent out about all the deadlines and the policies for how things are going to work now. And please stay healthy, please stay safe, and try to keep your spirits up. I know this is a crazy time, but we're all working really hard to keep your education going. Bye, everybody.